Hi everyone. Welcome to Math Spellbook. I'm your host Peter. So I won't be on my camera or my VTube model today. So basically, I just thought, if I'm not gonna show my face on camera, I might as well just basically start streaming, cause you're here for the knowledge, not here for basically just me popping up on screen. But I just thought basically we would get back to covariant and quadravariant vector components. So I've been doing a little reading this morning, and also Sasha also because of his awesome lesson yesterday, I just felt as if we should jump in and basically just start doing some stuff. So I did read a little bit about quantravariant and covariant vector components, and I feel as if I'm sort of getting closer to understanding how they work. At the same time, it's sort of like I feel like maybe with this study session we can be a little bit more productive on actually understanding how they work and probably how to use them and how to understand how the problems within them work. And maybe we'll also learn some linear algebra along the way. And also I think I'll add another book to our lineup because I'm using my web browser here. But how are you guys doing? It's Wednesday. You made it to Wednesday. Congratulations. It's the middle of the week. Hopefully this will prove to be quite enlightening to you guys. I know basically with my streams I've been doing vectors a lot, but vectors is the first thing you learn in physics, and I felt as if the way they teach vectors in physics, it's good for basically getting you into the physics right away, but then you realize that there's different types of physics, such as fluid mechanics, general relativity, and all that stuff, and it's the space around the vectors kind of they don't change the vectors, but they kind of manipulate them in some way, based on our own observations. So I felt as if I had to learn a little bit more about vectors. So that's why my content is mainly a lot about vectors and all that stuff. I do series too, but at the same time it's I feel my whole mind is a big mesh of figuring out, okay, this week we'll do vectors, this week we'll do series, and this week we'll probably do differential equations or whatnot. But I pull them out one at a time, but at the same time it's not in a particular order or a particular curriculum. So I think that's how it is with my brain sometimes. It's I get these random pieces and then I basically just piece them together in some way, and then I basically try to come up with why is it that the connection exists, or at least why is it that my brain interprets said connection. So let me find this other book. You guys are familiar with it if you have watched the channel for a while, and if you're watching this on YouTube, don't forget to drop a like, comment, and subscribe. The usual three. And if you're watching this on Twitch, and if you like math content, as well as maybe just a productive stream to keep you busy, to do the artwork you need to do, or to basically get yourself productive on anything, be sure to drop the channel a follow. Hey Sasha, how's it going? Yeah, we're decided. So what's the best part of your day so far, my friend? So we decided not to go with the camera today or my VTube model, because I thought we would just basically just focus on the knowledge. And also I would personally like to thank you, Sasha, for making these notes. I think these notes are pretty helpful, because I did read a little bit, but I didn't finish reading them, so I thought I would finish reading them on stream today so that we can get a better idea. And also I have a little bit of a linear algebra book, and if you can tell by the title, basically we're not playing games with linear algebra. And we also have a book on vector calculus too, so if anything interesting with vectors comes away, we'll probably take a look at this book too. And we also have our typical book, Student's Guide to Vectors and Tensors, and we were reading this book, and I read a bit of this book this morning. I feel like I'm starting to understand covariant and contravariant components a little bit better. Although I can't say 100% certainty that I would say I fully understand it yet, but I think these visuals are very cool. So these visuals are basically they help illustrate quadravariant and covariant vectors pretty visually, and I think I like that. So basically we have a light that's basically pointing parallel to the x-axis, and we have a light that's pointing parallel to the y-axis. So basically this is like the projection of what happens if the projection of the shadow is onto perpendicular to the axis in question. So going further down, we also have this light, which basically is like when it's perpendicular to the axis in question, we basically get more different components. And then when we actually do these together, we realize that there's a mismatch. So from what I understand, this picture is when you basically have the light shining upon like I think parallel to the axes. Let's see. Yeah, these are parallel. So these are parallel to the axes. And these are the ones that are perpendicular. And the ones that are perpendicular, there's a big mismatch here. So I'm thinking mainly the ones that are parallel, those are quadravariant, and those that are perpendicular, they're covariant. Or maybe it's the opposite. Let's see. I think it might be the opposite. This behavior causes perpendicular projection components traditionally with covariant. Okay, so perpendicular, which is this one. Is it? This one is, yeah, this one's perpendicular to the y-axis, and this one's perpendicular to the x-axis. Okay, so this is the perpendicular one. So this is the covariant, and this is the quadravariant. Eating pizza? Nice, Sasha. Congrats on the eating pizza. Pizza is always a plus. And the parallel projection components is the quadravariant components. Okay, so at least we have a visual that helps us. So if it's perpendicular, then that means if it's a perpendicular projection, it's probably a better way to visualize that than for covariant components. So basically I'm thinking that since this is parallel, but it sort of like matches the distance based on the axes, I'm guessing that quadravariant is basically related to the axis or the coordinate system in question, whilst covariant is more associated with, if these are perpendicular to the, so it's reflective of, like, I'm trying to think of good words to phrase it, because I feel like I have the idea in my head. It's just that solidifying it in one sentence, aka if you're taking notes, summarizing it in your own notes, is the hard part. Because we got the projection from perpendicular to the x-axis here, and then we have the projection perpendicular to the y-axis. So these are perpendicular and these are parallel. So I'm guessing quadravariant is the vector components that go with the space, whilst covariant is the components that For some reason, I'm thinking that, like, when you think about quadravariant, it's sort of like this is how it is. This is how the vector looks globally, and then when you think of the covariant, this is how it looks globally. I don't know if that's the right way to phrase it, because I keep thinking that since like the light, at least like in this image, since the light is practically like perpendicular to these angles, I kind of feel as if it's like this one is like a more like bird's eye view of the vector compared to like the whole entirety of the space around it. Whilst this one seems like it's like, oh, I'm measuring it from my perspective from the origin. I mean, that's how I'm compiling my thoughts right now, but maybe like further down the line we can probably like come up with a better way of summarizing that. Oh, I forgot to put the study timer up here. Yeah, like this week has been nothing but like reading and researching, formulating, compiling our thoughts. I mean, if I'm wrong, you guys can, if I'm making the wrong assumptions, you guys can correct me in the chat. So now we're up to dual basis vectors. All right, dual basis vectors. Okay, you guys can read it. I was afraid that the chat and everything else is blocking it. Okay, so what do we got? For non-orthogonal coordinate systems, it's clear from the geometric considerations such as those illustrated in figure 4.12, which is this one, that perpendicular projections of the vectors onto the coordinate axis do not form components in the way that the parallel projection does. Okay, the perpendicular projections simply don't add up as vectors to give the original vector. But to truly understand the process of adding up components as vectors, you have to think about the role of basis vectors in addition to that. To see how that works for parallel projections, take a look at the vectors E1 and E2 pointing along the non-orthogonal coordinate axis in figure 4.14, and the projection vector A onto those directions. In this case, vector A may be written as 14.13. Okay. The important key word for dual basis vectors is the dual vector space. Yeah, because I remember you were talking about we were talking about vector spaces like a little bit yesterday, in addition to Monday as well. So thank you for reminding us of that big, broad, big picture view, Sasha. But yeah, like I don't know if what I said before was, I guess, not, I wouldn't say it's the correct way, but sort of like a certain way to view it, because I said that quadravariant, like the parallel projection, is similar to saying that this is how the vector would look locally to an observer standing at the origin, like, you know, in the space, whilst covariant seems like it's the vector's projection on someone that's looking at the space from a bird's eye view. So it's like a global look at the vector in the space. Because the vector is supposed to be the same in both perspectives. It's just that I think the perspectives are a little different. That's why I think like quadravariant is probably like, I guess, like kind of linked to the word locally, whilst covariant is kind of linked with global. I mean, that's how I see it, but if it's like not the right wording, I'll try to work on that. You can let me know if I'm getting the wording a little bit off. So it's written like this. Okay, so this one is a parallel projection. Parallel to the y-axis like that. Okay. Okay. And it could be written like this. And we have the subscripts here, so... And we have the superscripts. So now we're actually going to get into index notation at this point. Where AX and AY represents the parallel projection of the quadravariant components of A. The same approach doesn't work for perpendicular or covariant components, AX and AY. Yeah, I remember seeing this notation before, and I'm like, okay, like, I'm kind of seeing what it's getting at. So basically, these are the basis vectors, but they're kind of like represented in the, I guess, opposite way with the subscripts and the superscripts. As you can tell by looking at the lengths of the projections in figure 4.12b, which is this one, it's clear that those two components multiplied by a basis vector E1 and E2 don't add up to A. So it's reasonable to wonder if the alternative basis vectors that would allow the perpendicular projection components to form a vector in the matter analogous to equation 4.20, which is this. Happily, there are those alternative basis vectors are called reciprocal or dual basis vectors. So let's see, basis vectors called reciprocal or dual basis vectors. Okay, dual basis vectors. Dual basis vectors have two defining characteristics. The first is that each one must be perpendicular to the original basis vectors with different indices. Okay, I'll reread that again because I feel like that was something that kind of went over my head a little bit. The first is that each one must be perpendicular to all original basis vectors with different indices. So that we call the dual basis vectors E1 and E2 to distinguish them from the original basis vectors E1 and E2. You can be sure that E1 is perpendicular to E2, and thus perpendicular to the y-axis in this case. Likewise, E2 must be perpendicular to E1. Oh, so it crosses. That's interesting. Oh, you typed something, Sasha. What'd you type? So if you have vector space, let's say for the sake of concreteness, it's R3, you can form R3 star called a dual space. The element of the dual space in linear functions of the form L or the linear transformation from R3 to R. Okay, so I'm trying to remember dual spaces. So is a dual space basically the same space but a different, I guess, vantage point of viewing the vector? Is that a good way of phrasing it? It's like the same space, but at the same time, it's like you're looking at the same physical space, but it's like it's dual space because it's considered, like, I guess, a different perspective of the same space, or a different angle, as it were. For example, L could simply be sometimes like as an x1 projected along the x-axis. No, that's not the same space. Oh, okay. Something star. Oh, something. Oh, okay. Element of that space are functions. Oh, okay. Yeah, I feel like we're getting closer to understanding these things. It's just that we just need that one little thing that basically, whoop, we got it. We're like eureka moment. There is a way to geometric way of understanding it. Oh, okay. Alright. So where were we? Oh yeah. So okay. So basically E1 and E2, they basically have to be perpendicular to the opposite of their counterparts, which is very interesting. Thus perpendicular to the y-axis and thus perpendicular to the x-axis. The directions of the dual basis vectors E1 and E2 is shown in figure 4.14. Oh, okay. So this is, oh, so this is perpendicular to the y-axis here, and this is E1. So that means like E2 that's pointing this way. Okay. Let me have an E1 right here, which is supposed to be the way to interpret this. And the light ray perpendicular to, so that we have E2 here, is pointing that way. And that is perpendicular to the x-axis. Okay. So perpendicular to the y, but okay. The second defining characteristic of a dual basis vector is that the dot product between each dual vector. Okay, maybe we can take some notes on that. So let's open this up. Hit pencil. Is it the right thickness I want? I think so. So dual. Oops. Yeah, dual basis vectors. I know I don't. I said I said that I don't like taking notes. It's not that I don't like it. It's just that sometimes I just fixate on the writing and I don't fixate on the substance of the notes. But I feel as if this is probably something we can keep in mind. Okay, so the first part. Okay, so the first part is. Okay, distinguish them from the original. So each one must be perpendicular to all original with different indices. Okay, so must be. Does this equation remind you of something? Yes, it reminds me of what we went over yesterday, actually. Where is it? I think it's somewhere here in the notes. Yeah, I think it's this part right here. Like the way it looks, yeah. It reminds me of this part. So this is the dual basis vectors. We were getting into dual basis vectors. So must be, I think it said perpendicular. Must be perpendicular to all original basis vectors with different indices. Perpendicular to all original, I think, components. Original basis vectors, okay, with different indices. Basis vectors with different indices. And then we'll put the example here. I'm trying not to write it note for note. Perpendicular. Oops. 1. Okay. I'm not gonna draw a graph or anything. I'm just like making sure that I keep a note of that, because I think that's like the cool part of it. Okay, and I think we gotta do the second part. So the second part of it, so we put 1 and 2. Okay, the second defining thing is for dual basis, the dot product between each dual basis vector and the original basis vector with the same index is equal to 1. Okay, so the original and new basis vectors with the same indices must equal 1 through the dot product. Okay, at least we're formulating our own notes. And then we just put example here. And it's basically, so E1 dot E1 equals 1, E2 dot product E2 equals 1. Okay. This means that you can find the length of the dual basis vectors as long as you know the lengths of the original basis vectors and the angle between each dual basis vector and the corresponding original basis vector. So to find the length of E1, you simply have to multiply the length of the original basis vector, okay, by the cosine of the angle between them. Oh, okay. So the length of this one would have to be, oh, okay, that's, so the angle between them, interesting. Let's see, lengths of basis vectors through their dual basis vectors. So if we have E1 here, we have to have the cosine theta 1 is the angle between between E1 and E1. And then we would just write the same thing for E2 in this case. With the concept of dual basis vectors in hand, you are in position to understand why perpendicular projections covariant components AX and AY may rightfully be called components. The key is that the projections must be made onto the direction of the dual basis vectors rather than onto the directions of the original basis vectors. If you do that, then the covariant components AX and AY can be multiplied by the relevant basis vectors and added to get the original vector A, in the same way as can be done using the parallel projection covariant components AX and AY. The covariant component is equivalent to... Okay. You may guess the use of superscripts to denote the dual basis vectors E1 and E2 is not accidental. When these basis vectors are transformed to a new coordinate system, the inverse transformation matrix is used, as it is for the quadravariant vector components AX and AY. Note that in the two-dimensional coordinate system with the orthonormal basis vectors, such as I hat and j hat, the dual basis vectors are identical to the original basis vectors, along with the coordinate axis. That's easily understood because of the direction that each of the dual basis vectors must be perpendicular to the direction of one of the original basis vectors, and hence must point along the x and y axis. Yeah, I'm just reading out loud like majority of this stuff because I just want to make sure that I didn't miss any details here. So the dual basis vectors are basically vectors that are perpendicular to the opposite of, or to the other indices, because they have to be perpendicular to them. Whilst the ones with the same indices, they have to make sure that the dot product between them is 1. I mean, that's how I can summarize it, but like, I'm just having a hard time actually, like, I guess visualizing how they work in the physical world, or at least like how we can view them in, I guess, like in a intuitive physical way that we are familiar with. And I know with math that's very, very difficult because sometimes like math is just very, very abstract to the point where it's like I can't even imagine this. All I'm seeing in my head are just probably like lines on paper. I'm not really seeing you know, like how dual basis vectors are equitable, if that makes any sense. Like, I mean, they do have applications. It's just that I don't have a current visual in mind to actually see how they work, like in I guess like in a physical or I guess mechanical sense. And since the length of the dual vectors must equal the inverse of the length of the original basis vectors times cosine. In this case, the dual basis vectors have the same length as well as the same direction as I hat and j hat. So the difference between original and dual basis vectors disappears for orthonormal like I can't really say that word that well, coordinate systems, just as the distinction between covariant and quadravariant components disappear for such systems. The concept of dual basis vectors can be readily extended to 3 dimensions, and in that case determination of the length and direction of the dual basis vectors is most easily done using the dot and the cross product between vectors. Okay. That is very interesting. cross product of those, and then you... Very interesting. And I'm guessing when you get the... When you're doing the covariant, it's the same way, only with the quadravariant, versions of these. Very, very interesting. I guess we can write that down. So what is... So it's just getting the vectors of the actual vectors. So let's bring this down here. Using dual basis vectors to find each other. So E1 goes E2 cross product, E3 1 dot product of down here. This one is 1, 2, and then we have E3 dot product. I think that's how it's written. Make this dot a little bit bigger. Oh. Oh, probably have to change that. Yeah, because I remember when it's the dot product, when it's the cross product of, say if you're doing the cross product of A times B, like the way it's written, if you think about it, it's like so the first one, if I remember, was Y and Z, so it's like AY BZ minus AZ BY, and that would be I, and then plus AZ BX minus and AX BZ J hat plus AX BY minus AY times BX K hat. I mean, that's usually how I remember it. Like, I remember, like, back then, they would probably, like, move, I think they would move AX to the front here, but that made it a little bit more complicated because there would be a minus sign here, and I was like, you know what, let's just take I'm just gonna write it the way, like, so we can remember it's just plus plus. I mean, that helps me out a little bit better, but, like, if you guys memorize it, like, the other way, then that's also fine. It's like the way, it's like the way you basically can, interpret it however you wish. Okay, let's see, each denominator is a triple scalar product of the original basis vectors. You may recall in section 2.3 that the volume of the picoforms of those vectors. In these equations, the cross products in the numerators ensure that the first character characteristic of dual basis vectors is met. Let's see, in these equations, the cross products in the numerators ensure that the first characteristic of the dual basis vectors is met. For example, is perpendicular to... Okay, so if you have multiple basis vectors, they have to be perpendicular to every single one of them. The triple scalar product... The computation of the dual basis vectors may seem long track. Yeah, you telling me. Like, reading all this made my brain go wibbly wobbly, timey wimey. Okay, so vector A is equivalent to these setups here, which serves to emphasize the important fact: if you seek to define the quality such as a vector A that remains invariant under transformation of coordinates, you have a choice to combine the superscripted quadravariant components and the subscript covariant basis vectors, or you can combine the subscript covariant components with the subscript quadravariant basis vectors. That would seem reasonable to you because covariant quantities transform using the direct transformation matrix, while the contravariant quantities use the inverse transformation matrix. Multiplying each of these quantities guarantees that the result is unaffected by the transformation. You can see an example of dual basis vectors and covariant and quadravariant components are determined in the next section. Okay, so what did we learn? What did we learn so far with that section? We learned what dual basis vectors are. Now I have to formulate my thoughts on them because they're defined by two things. The first thing is that they have to be perpendicular to the other basis vectors, to the original coordinate system that we used. In addition, these new basis vectors must also equal to 1 by the same index of the other coordinate system, by their dot product. This is how we find the length. And this is how we find the basis vectors of the other system. I mean, practically, if you know the coordinates of the basis of one, you're more likely to find the other. I wonder what problems we'll run into with these. Okay, here we go. Finding covariant and quadravariant components. I have a cough drop in my mouth, guys, so I apologize if my voice sounds a little bit, like, it doesn't sound as, vibrant on the mic. Okay, once you grasp the concept of dual basis vectors in non-orthonormal coordinate systems, finding the covariant and the quadravariant components of a vector is straightforward. As an example, take a look at vector A in figure 14.15 with non-orthogonal basis vectors E1 and E2. Okay, so this is the non-orthogonal basis vector. Let's let's see, the parallel projection onto the basis vector. So this is perpendicular to the x-axis. Because if we shine a light and then basically go here, and this is from the perspective of the actual angle made by E1 here. Let's see here. So this is A2 and A1. Which can be just written as two equations. This one looks familiar too, from Sascha's notes here. Because I think this is when we were defining a metric here, or at least like on our basis. So we have this here. These two simultaneous equations may readily be involved for A1 and A2 using the elimination and substitution method, both of which are demonstrated in the online problems at the end of each chapter. So E1x E2 and x 3. This is E2. Now I'm trying to think about, I'm thinking these are like the differences between, like, you know, from E1 from the X perspective and E1 from the Y perspective. And I think these are like similar to what Sasha taught us yesterday, which is, where was it? We had it here somewhere. Like these here. Because this is, yeah, the differences. And this is a difference one as well. So, am I safe in thinking that these, or at least the notation at least, is similar to what these are? I mean, they look similar. Although I don't know though. I mean, they look remarkably similar though. Alright, so these two simultaneous equations may readily be solved for A1 and A2 using the elimination and substitution method, both of which are demonstrated in the online solutions and problems at the end of this chapter. Another approach is the matrix method and Cramer's rule, described in the matrix algebra review on the book's website. Okay, so this is more linear algebra stuff that we have to practice. Using this approach, you begin by substituting the known values of A as well as E1 and E2. Okay. So I'm guessing they're using an example here. Then, ooh, that looks cool. Actually, I probably should look up what Cramer's rule is. I've heard of it, but I keep forgetting what it is. Cramer's rule. Alright, what is this? Cramer's rule is an explicit formula for the solution of a system of linear equations with as many equations unknowns valid whenever the system has a unique solution. So we have the determinant of beta. That doesn't tell me much. I need to see a picture. Oh, okay. So let's see. A is 1, 3, 2, 2. A1 is 5, 6, 3, 2. And A2 is 1, 2, 5, 6. I'm guessing you use the determinants of that. But the one thing I don't get is that with this example here, let's see, this one's A1, which is, yeah, that's and then green, that's 6, and then the -4, right? This one here with this one here. So A1 in this case, you have to take away this one and then make this into a matrix. But why is it that this one is in front and this one's on the other side? What happens if you switch them? So then we would have, so if you switch this, then 18. So 10 and 18 minus 8. Yeah, okay. So it doesn't matter. Preferably, I would have just put the 3. I would have just left in this back here. I would just left this over here, so that way it would have been like 3, 2, and 5, 6, and then just cross. And yeah, it wouldn't be any different. And then basically, oh, you get X on this guy, so you get the variable over here. So I'm guessing, so the variable here, so it would be positive 2. Okay. Oh, okay, so that's what Cramer's rules is. Alright. Okay, I see you. I see you. So basically, oh, okay, so when you think of linear transformations, like if you want to get the matrix. Sorry, guys. So imagine if you actually had this and this, but you didn't have this. Actually, if you come up with this, I think that would probably give you like how the space is defined at that point. Because the thing of it is that I don't think there is division in matrix arithmetic, or at least in matrix algebra. I have to like actually review my matrix like operations actually, because I remember there's addition, there's multiplication, there's addition, subtraction, multiplication, but I think division is not really in the ballpark. And it's break time. Okay, I think we're making some good progress so far, guys. So if you guys need to get a drink, need to like relax, chill out, get a stretch, you're more than happy to do so. But I will be right back. Just give me one quick second. I will let you guys know when I have returned. Alright guys, I'm back. Sorry to keep you guys waiting. Like apparently like before I started streaming, like before I got on, they were flushing out the hydrants. So like we didn't have water for like a good like hour, so I would have to like I had to actually like wash the dishes, like because we got our water back. So you know, it's one of those things. Like hopefully you guys weren't waiting too long. But tell me how your guys' week has gone so far. Hopefully you guys have been going, hopefully you guys have had a good start to your weekend. You guys basically have to make it to the weekend if you guys are looking forward to the weekend. I'm probably gonna like see like one of my cousins this weekend, cause she flew in from California and she brought her son with her. I actually bought her son like just like a few minutes ago. I went on Amazon and I bought them like baby books, like quantum mechanics for like babies, like general relativity for babies, like all like basically I think it's like Newtonian physics, quantum mechanics, general relativity. I have to take a look because there's 4 books. I didn't like. I saw the bigger version, and like they had more books in the bigger library version, but I was like, no, I can't have them bring that back to California. That's way too much. Yeah, we got like quantum mechanics, Newtonian physics, quantum physics, Newtonian physics, rocket science, and general relativity for babies. That's a pretty good curriculum. I don't know if her son's gonna like it, but you know, like I thought, why not just have that, like, you know, because like I probably might not have kids because I don't think I'm gonna be that lucky to meet someone that I can spend the rest of my life with and have a child. But you know, like with my nieces and nephews, I feel as if like I can try to at least get them into like this, like the cool part of STEM, like, you know, like how I was affected, because I know with school and everything, like kids are not inspired to get into math because they're so into the technicals of how to calculate things and how to memorize things in school, which is unfortunate because school is meant to educate our kids to be thinkers instead of just being memorizers and calculators. But I think it's because of like how school is like kind of making kids more into employees, because like, you know, governments and societies benefit from that. So it's like, you know, it's up to the kids whether they decide to rebel. It's like, no, I'm gonna be a business owner, or I'm gonna be an entrepreneur. I'm gonna actually learn how money works, and I don't need like an institution to tell me otherwise. You know, that's like, you know, that's like basically like being a maverick and just basically just trying to learn things that the system, or well, when we say the system, I mean like typical society wants you to believe, you know. That's why I like learning things about like finance, because not like in the academic sense, but mainly like how things work in a practical sense when it comes to like economics, finance, and money in general. Because when you learn how like the rich basically like find ways to like eliminate certain taxes on their tax returns, you begin to realize that, oh, the system is set up so that they benefit from it in some ways. And of course, like many people will basically say that the rich need to pay their fair share of taxes, but at the same time, it's like there's so many things to the tax code that allowed them to like put money more into the economies that they're living in. So I think it's because like I think the reason why the tax code is set up that way is because it's usually kind of like, I guess, assume that people that have more wealth, they will redistribute the wealth into things like businesses and you know, places to live for people, as well as providing services that their communities can use to grow, you know. And of course, I do believe that there are some rich people that do that, because, you know, like I think some rich people are just tired of the most popular scandalous rich people getting all the bad rep. It's like, oh, it's because of you guys. Like, people think that we rich people are like snake salesmen and like conniving evildoers. and you know, like, of course, like, you know, like it's also like perception too, like how you view like certain individuals, like whether it be different classes, different cultures, and like, you know, different like trains of thought as well. So, you know, it's just something to be aware of as human beings, because we do have our blind spots. And I had to admit, I was kind of blind to the fact that, oh, like I thought the system worked one way, but then it works in another way for like different classes of people. And, you know, like the only thing that we as people want in a fair system is that everyone is treated as an individual. But of course, like, you know, a lot of people are very concerned when people have certain advantages, does those advantages make them above the law, which is something that we kind of don't tolerate as a society, or at least at least in American society we don't tolerate that, because we believe that the law is like supposed to be like the gold standard of like what it means to actually be a citizen. Like, I know I'm rambling a bit, but that's basically my thought process of what I've learned throughout my I guess my 35 years of life. I mean, I'm not 35 yet, but I'm about to be this year. But like, you know, also keeping your curiosity alive is also important. And you know, that's why I still like try to learn as much math as I can and try to learn as much physics as I can, even though I'm not good at solving problems involving both subjects. But like when I read it, I feel as if I'm kind of tapping into kind of like the underbelly of what it means to actually see an abstract world where you can find the beauty in creative logic. And I think that's the thing that makes like science and mathematics very appealing to people, because it's like once you are able to see the patterns that scientists and mathematicians see, you begin to feel as if like you're more connected with the things that you kind of like taken for granted, like why is the sky blue, or why is a flower like blossoming with like a couple patterns within its petals, like the Fibonacci sequence. Hey Penn Center, how's it going? If you guys are not familiar with Penn Center is another awesome math streamer. They do a bit of a lecture series on linear algebra in addition to real analysis. So be sure to check out Penn Center's content and give Penn Center a follow, because sometimes I might pop into their streams whenever they are alive. So, you know, I will be in the classroom with you once they start doing those things. But how are you doing, Penn Center? What's the best part of your day so far? Are you discussing math philosophy? It's to look at nature and not be inspired to believe in God or the universe. I guess you can say that, because for me, I was just basically talking about how, I guess, like, once you try to open your mind to like study things in STEM, in addition to things like spirituality and outside of things of STEM, you begin to realize that there's a big ecosystem with all the knowledge you've gained. And I think it's sort of like it forms into this nice small ball within your brain. Because like on my downtime, not only do I try to put my effort to read more about math and physics, but also about finance. I just recently bought a book on debt, which I'm kind of excited to read, because it's a book about like how the rich use debt to get wealthy, which I think is a really interesting book. I also found I also am waiting for another book that I ordered, how the rich know about the tax code. So I think that's also going to be a fun read to read. But yeah, like I think, yeah, like what I was discussing before was basically like how occurring all the knowledge that I've gained over, like, you know, over my, I guess my 35 years of being on this earth, I feel as if I feel like I'm being more connected the more I try to open my mind to like different perspectives and different ways of viewing the world, because like I still believe that the world is dominated by like a platonic mathematical realm that is like neither seeable, touchable, or even smellable, that is somehow able to construct like our physical universe and stuff. But at the same time, that's not a proven fact. It's just basically what I believe. It's like I feel like math is kind of like the underbelly of patterns, and I feel as if like there might be a world of like I think like I've been converted to Edward Frankel's way of viewing the world, is that he believes that there's a world of mathematical ideas out there, and we just have to go look and find it. Because I think for him, he doesn't subscribe to Max Tegmark's mathematical universe hypothesis, which is another thing that I kind of feel like I want to embrace as well. But I think like Edward Frankel's like view on how mathematics is like sort of like the patterns that lie within our physical reality, but even though it's not part of it, it's integral to like the nature that we see around us. That's like me putting spirituality into it, mainly. I'll just turn that off. I want to see what you guys type up. My day so far has been marking the Euclid test. Nothing super exciting. What's the Euclid test? But hoping to do some gardening in a bit. Maybe stream after it goes to work. Oh, I see. It's always helpful to try to see the world in many ways. It helps us grow as humans. Right. I agree. Yeah, like I'm more of a spiritual type of person. Like, it may seem weird, but like for me, it's like I usually think of like, say, like if you're, like obviously everyone that basically works like has a bank account and like they have like money to spend. So I usually think of money as sort of like energy. Like when you spend money, you're giving your energy. When you gain money, you're gaining energy. And the thing of it is that I think the more spiritually in tune you are with yourself, I feel like the wealth eventually comes. Like I know it's silly, but like I've read Ken Honda's book Happy Money. It's a very great book, I think, because it works with me, but some people might think it's just mumbo jumbo. But mainly it's about like you treat your money as if it's a separate entity, like basically like an energy source. So like whenever I spend money in my mind, I thank the money. Whenever I gain money, I basically thank the money as well. So, you know, I know that's like kind of weird, especially for a math channel. but you know, like I put a little bit of myself in each stream, so you know, that's a little tidbit you guys have learned about me. The Euclid test is grade 12 math contest hosted by. They always ask me to help mark each year. We're almost marked for the first batch of 3,000 tests. Wow, that's crazy. Must be a pretty tough test. Sheesh. Okay, before we start our next study session, guys, I will be right back. I'll tell you guys when I'm back. Don't worry. Okay guys, I'm back. Sorry to keep you guys waiting. Alright, now let's get back to covariant and quadravariant vectors. So study timer is on and let's get into it. I'm just gonna pop another cough drop. Let's see. So we're going over Kramer's rule. So the thing is that with Kramer's rule, so you can't use Kramer's rule to actually figure out what this is, because when I think about it, you actually need this in order to I mean, you can multiply this and then you would have to divide these two. I have to remember how division works with matrices. Because I don't think you can divide with matrices, can you? Oh no, these are oh no, these well, these are determinants. These are determinants though. Yeah, I don't think you can divide by matrices. Right, okay, yeah. That's what I thought. You can divide determinants as long as the denominator is not 0. Right. Yeah, because I'm thinking, because like since we're dealing with covariant and quadravariant components, usually the transformation matrix is the thing that's the most important, because it gives us the defining altercations to the vector from one I guess like one coordinate system to the other. So I'm trying to think creatively here, and I'm like, there must be a way to like get this matrices by using, like, if you know the two vectors that's being multiplied by the transformation matrix. That's just a question to keep in mind. I'll just put it in my mind palace and we'll just sort it out, and hopefully when we read more we'll probably find the answer. Let's see, to use the same process to find the perpendicular covariant, you must first determine the length and direction of the dual basis vectors. You know that the direction of A is perpendicular to. Oh, okay. I thought I said E2 to E2, and I'm like, no, that should be right. The direction of this is perpendicular to E1, so we get the length there. Then we can use equation 4.21, which is this. Okay. To find the length of the vector. Okay. Let's see. Find out the angle between. If you look at figures 417, you should be able to determine the arctangent was out. You can see a very short dual basis vector. So once you have the dual basis vectors in hand, you're in a position to find the perpendicular projection, the covariant components of A1 and A2. You can do this by continuing the perpendicular projection line beyond the direction lines of E1 and E2 and onto the direction lines of E1 and E2 as shown in figure 4.17. The magnitude of A, okay, the angle between A and the x-axis is 2/7. The arctan of 2/7. So, okay. You can determine the angle between A and E is, and the angle between A and E2 is 15.41. Okay. So this is it. Oh, okay. So L1 is Yeah, when it comes to like stuff like this, I get like so overwhelmed because I'm like, oh my gosh, this is not typical for me to see. It's like it's not 90 degrees. It's not perfectly 90 degrees. It's not. It's like basically like a lot of like triangles over triangles, and I'm like, oh my gosh, which one should I concentrate on first? It, like for me, like when I see stuff like that, it reminds me of like what do you call it? A schematic for like a machine of a motherboard's a motherboard schematic. That's what kind of overwhelms me when I see stuff like that, especially when it's like trig and you see like triangle after triangle and you're like, oh my gosh, like where is this going? So we got line 2, line 1. So this one seems like it's more clever maneuvering. Yeah, they're giving a lot of like numeral examples in this part. I mean, Cramer's rule is important in this section. Okay. So they like the first sentence of this last paragraph basically sums up what's going in my head. It's like, and if you're wondering why you might go through the effort of finding some of those components, rest assured that the payoff is worth the effort. To appreciate the value of that payoff, you'll have to begin thinking of vectors not just as arrows with a certain length pointing in a specific direction, but rather as a member of a class of objects called tensors that have a very predictable and useful properties under transformation of coordinates. In that view, the vectors you've been dealing with up to this point have all been tensors of rank 1. See them as such and understand what that means will be made a greater deal easier through the use of the notation called index notation and a convention known as the Einstein summation convention. Index notation. I think we got familiar with this like the last 2 sections. Yeah, I remember the Einstein summation convention was like basically like Einstein was so proud of himself because he just took away so many summation symbols from his own formulation. And now I think like everybody, including mathematicians, use it, which is pretty ironic because it was created by a physicist just for convenience. Seen the first glimmer of index notation in the earlier section of this chapter described by coordinate transformations. As you may recall, the angle between the transformed rotated coordinate axis and the original non-rotated axis of the two-dimensional coordinate system were known as alpha 1 1, alpha 1 2, and alpha 2 1 and alpha 2 2. These angles could just as well be designated as is that an alpha? Yeah, it's an alpha. Because like from far away it looks like an A, and I'm like, are they using A or is it alpha? Yeah, I think, yeah, it's A. I mean, it's alpha. So it's alpha XX, alpha XY, and alpha XY, YX. And the like, but there's several good reasons to use the index number 213 rather than the coordinates. Just make it more convenient just to use the numbers, yeah. Because then you would run out of letters if you went into higher dimensions. Okay, designated elements. I'm guessing this is like a matrices. Like if you can make a matrices out of this one. Yeah, I remember when I first read this book, this section was the thing that kind of like knocked me off my rocker, because I was like, wait, what? I was like, wait, what? What is this? What is this part? What does that mean? Whenever an index appears twice in the same term, once as a subscript and once as a superscript and once as a subscript, you can omit the summation symbol and simply write okay, in which the reader knows to sum over the repeated index J in this case, such as the repeated index are often called dummy indices, since any letter may be used for that index and the result will be the same. It was Albert Einstein, yeah, his greatest discovery in mathematics. Yeah, I remember that, yeah. What do you call it? The idea of a certain result. Before moving on, you should take a careful look at the equation. Okay, and make sure you understand that these few symbols mean exactly the same thing as many terms in separate equations. Okay. So A1 would be changed. So A2. Okay. Oh, that's a short section. I thought it was longer. They tell you that each component in the prime coordinate system is a weighted linear combination of the components in the original unprimed coordinate system, with the transformation matrix element A. Now I'm getting myself. Oh, that looks like it says alpha, and I think this says A. Okay, because I thought it was alpha again, and I was like, what? Providing that the weighting factors for each term, and if you want to know the exact meaning of each of those factors in the transformation of covariant and quadravariant vector components, the next section will help. Okay, here we go. Quantities that transform quadravariantly. Okay. With convenience of index notation and summation convention at your disposal, you should be ready to take the next step in the transition from thinking of vectors as quantities with magnitude and direction, just understanding why vectors belong to the class of objects known as tensors. That step begins by asking the question of how a differential element such as ds transforms from one coordinate system to another. And I'm guessing like a ds, that is supposed to be like a line in space, like or at least the length of that line. In general, the equations, ds is the metric. Oh, okay. Because I remember I would see ds when they did like the Pythagorean theorem, like, you know, a squared plus x squared plus y squared, all that jazz. Let's see. In general, the equation relating to the coordinates in one system to those in another do not involve a simple linear combination of coordinate values. For example, in transforming the spherical to the Cartesian coordinates, it's not possible to write the equation such as x is equal to a11 r plus a12 theta and plus a13 phi, because x depends on the product of r and with the sine and cosine of okay. Oh yeah, because it's spherical coordinates. And y and z are similar in a non-linear relationship to spherical coordinates. However, you ask how differentials of x and y and z, that is dx, dy, dz, depend on the differentials of r for radius, theta, and phi. That is that dr, d theta, and d phi. You'll find that on this infinitesimally small scale, dx does depend linearly on dr, d theta, and d phi. Okay, we went over this yesterday, Sasha, I believe. We went over some of this. So, likewise, dy and dz. Okay. For any two coordinate systems in which the linear relationship exists between the differential length elements, writing the equations which transform between the systems is straightforward. If you call the differentials of one coordinate system dx, dy, and dz, the other coordinate system dx prime and dy prime and dz prime, the transformation equations from the unprimed to the prime system come directly from the rules of partial differentiation, as shown in the left column below. Okay. Oh, okay. Let's see. So basically you have to take like the primed, this is taking spherical coordinates and turning them into, or is it taking the Cartesian coordinates to the spherical coordinates? Because I think the prime ones are supposed to be the spherical coordinates, right? So it's, let's see, turns into dx1, dx2, dx3. Oh, this is the general script. Okay. So they don't have to use like y. I was like, what are they writing here? Okay. Here we go. Using index notation approach and substituting x1, x2, and x3 for x, y, and z results in the column shown on the right, putting into matrix notation. Okay. So, yeah, I remember Sasha showed us this yesterday, like this the Jacobian. Let's see the rows here. So basically every row is basically like first term, second term, third term, and we just keep going down the line here. Okay, we're using individual equations with the summation symbol. I mean, both look pretty intimidating, I will say that for sure. If you allow I to represent each of the numeral values of index 1, 2, and 3, this can be written as, just put an I there, and since J index is repeated, a final simplification results from the Einstein convention, allowing you to write. So when do we take away the summation symbol? I just want to go back and remember. Okay, final simplification. Whenever an index appears twice in the same term, okay, so there's a J here and a J here. Once as a superscript and once as a subscript, you can omit the summation symbol and write simply. Okay, so it's when we have a superscript and a subscript that's the same. Okay, that's good to know. That will save me a lot of ink because I use a fountain pen. Don't ask me why. I just love writing with a fountain pen. It just feels pretty cool. Like it feels like I'm actually kind of like going back into the way things were like long time ago. Yeah, the only conundrum with a fountain pen is that you have to keep filling the ink. Like before it was cumbersome for me, but then I just got used to it. Well, thank you, Sasha. I appreciate the compliment. I mean, writing math with a fountain pen does feel like I'm tapping into a historical, like kind of feels this sort of like I'm going back in time to where mathematicians were like basically scribbling a lot. Not really. I just wanted to actually have a fountain pen, so I was like, maybe I should buy a fountain pen, and I bought one, and I was like actually writing a lot more with my fountain pen. And then I eventually just got used to it. And I'm left-handed, so like fountain pens are sometimes like, it can be cumbersome if you're not careful. Because like since I'm left-handed, if the ink is not dry, my hand gets ink on it. Oh, that's what you meant by asking that question. Well, I mean, I do love your math content, Pen. If you're asking the question. So where were we? Oh yeah. Yeah, hopefully you guys don't mind. Basically, sometimes my study session's just me reading this stuff. Because, like, I know, like, you know, with math, you're supposed to do problems and practice. But for me, it's like, whenever I read sections about math, it makes me feel as if I'm kind of getting a better ground of actually, I guess, seeing things unfold. Like how mathematicians usually, like, see it within, like, I guess, a literary sense. Because the thing of it is that I always wonder, like, how would, if you had main characters in a story and they had superpowers and they can only use math to illustrate those superpowers, how would you best describe that to the reader who is not mathematically literate? I like your... OOT content too. I don't know what that is. Oh, okay. A Zelda game. Oh, okay. Gotcha. Yeah, even though I knew about Zelda, I never played it back then. Oh, Pen, you're just like an awesome streamer in general. You basically play games and also you help us in math. So, you know, you're like an awesome streamer in general. Compared to equations... Are they still making Zelda games though? That's a good question. Like if there was a Zelda reboot, maybe I would consider like playing. Because I remember back in the day when I was playing PlayStation, I played Crash Bandicoot. I think I didn't get into Zelda because I didn't have the Nintendo 64. I had the PlayStation. And I actually didn't ask for it. My dad bought it. And he wanted to, and I think he wanted to play video games because he thought it was a cool thing. And then like, yeah, because I never even asked for a PlayStation 2, PlayStation 1. And then like I started playing it and I was like, like, I mean, this, like, games are cool, but I wasn't really a hardcore gamer at the time. I love watching TV too much. I'd rather watch Saturday morning cartoons than play a video game back then. But now, like, I'm actually becoming a gamer. This tells you the components in the prime transforms. So let's see, vectors in the unprime original components. Are weighed by a linear combination of the components. So I just needed to reread that again, just so that I have a better idea of what I'm like getting into. Weighing in the factors. So if it's written like this, and it's the partial derivatives. Excuse me, guys. Sorry. So is A in this circumstance supposed to represent the metric? Because like, I'm guessing AJ is supposed to be one vector one vector in a coordinate system, and A prime of I is supposed to be the representative of another coordinate system. See, on the left side of both equations, the quantity of Okay, I made a dumb choice of notation. What do you mean? Are you talking about in your notes? Like, what do you mean by that, Sascha? I decided to call the projection map, though thereby. Oh, okay. Oh, hello. Lolly's. Is it Lolly? Is it Lolly Sally, or is it like Lalai Salai? Sorry if I mispronounced your name. I just want to make sure that I pronounce it correctly. But how you doing? How you doing? What's the best part of your day so far? Is it Lolly Sally or is it like Lolly Sally? Neither, but the first one was better. Lolly Sally? Lolly Sally? I don't remember which one I used. But the first one's better. I think the first one I said was Lolly Sally. Yes, no worries. Okay, cool. But what's the best part of your day so far, Lolly Sally? And welcome. I see it's the first time you're chatting with us. What brings you into the math spellbook domain? You like math, you like physics, or you basically just need a productive stream to keep you busy? Because I'm here for all three. I'm here for all three if you need it. Finish the big deadline. Nice, nice. What was the deadline? I mean, what did you need to finish, actually? What was the effort that you strenuously brought upon yourself to finish in this neck of time and space? I was trying to make it sound epic, but I guess I failed in the delivery of that. Oh, this is a lot of reading here. I like math, I like physics, but want to get better at maths. That's fair. That's fair. Me too. I want to get better at maths. I want to get better at maths so I can understand like the much tougher equations that physicists are trying to like use. Well, if you like math, if you like physics, like, you know, drop a follow if you'd like onto our channel. Like, I always try to do math every single stream in this channel. And if you're watching this on YouTube, you know, do the typical ritual of, you know, drop a like, hit subscribe, and leave a comment down below if you're watching this on YouTube. I always upload my VODs onto YouTube, so like if you've missed the first part, you'll be able to like rewatch it on YouTube. Because I know Twitch has like a time limit of like how long it holds VODs. Thank you for the follow, Lolly Sally. Much appreciated, much appreciated. Welcome to the Math Spellbook domain. If you would like to access our Discord server, you're more than happy to click the link in the chat, Lolly Sally. That way, like, you can get to hang out with us on the math server. Like, maybe talk about like ideas that you like in math and physics, if you like. Or just talk about life in general. Basically start up like a storm of chats. I try to be more active on my Discord server because I know that sometimes it's kind of dead. Like whenever I find a good video on YouTube about math or physics, I post it there. Probably help someone along the way. Okay. An equation 4.48. That is this one. On the left side of both equations, the prime quantity is... Okay, yeah, that is a prime. Okay, so dx prime I or a prime I with the free indices I appears. On the right side, both equations contain the product factor with a free index I and a dummy index j. Okay. Okay, they rewrote it here. Okay, that's good. On the left side, with the left side quantity unprimed and the dummy index j. dxj and aj. AJ, name. Name. And you know that the factor aij in the equation represents the element transformation matrix for quadravariant vector components between unprimed and primed coordinate systems. So it seems reasonable to conclude that dx prime I and dxj term can be seen as an element of the transformation matrix for differential length elements. Okay, so it's basically saying that this and this are practically the same in one way or another in structure. That's good to know. Can be seen as an element for the transformation matrix for differential length elements. So instead of looking at equation 453, can be seen as an element of the transformation matrix for the differential length elements. So instead of looking at simply the index notation version of the chain rule, you should see it as a transformation equation that takes on differential length elements from prime to unprime to the prime coordinate system. Okay. Let's see, equation 48, which is this one. Insight are not only elements of the transformation matrix from the prime to the from the unprime to the prime coordinate system, they are also components of the basis vectors tangent to the original unprime coordinate axis, expressed in the new prime coordinate system. Furthermore, you know that basis vectors tangent to the original coordinate axis are the covariant basis vectors described earlier. And since the quadravariant vector components combine with the covariant basis vectors to produce invariant quantities, differential length elements must transform as quadravariant vector components. This is the reason that the indices are written as subscripts. The differential length element is the prototype of the quadravariant vector components. Using index notation and representing the components of the basis vectors as, you should now understand why the transformation equation for quadravariant components of vector A is often written. Many authors resent this definition of quadravariant components. To see how this notation works in practice, consider the transformation from polar to two-dimensional Cartesian coordinates. In this case, I think this is gonna line up to what we discussed yesterday, Sasha. Okay, so we have to take the derivative. X to y. Yep. So E1 plus 1 like this. And I think this was also in your notes. Yep. Right here. Are really components for the tangent vector. So you can see that there's written components. The first of these expressions is a vector pointing radically outward and along the r hat direction in the polar coordinates. The second is the vector pointing perpendicular to radical direction of the theta hat direction. This demonstrates the partial derivative do indeed represent components of the original unprimed covariant basis vectors expressed in the new prime component coordinate system. Boy. For all you guys that are doing research for your PhDs or masters, I'm like, how do you guys like still remain like focused on like looking at page after page of content? that's like the real question. I mean, it's exciting though. I'm getting excited, like just basically finding the connections here. But at the same time, like, I don't know if I can make a full-time career doing that. It's like being a mathematician or being a physicist or a mathematical physicist or whatever field in STEM or math. Like, I end up wondering, it's like, dang, you guys have such resilience to be able to look at a page for like hours and try to keep questioning yourselves in the head on like, is this the right approach, or is there a way I can actually be creative and like manipulate this particular operation into my advantage to come up with, to actually see an idea or something beautiful within the math or within the science. Actually, Lolly Sully, like, since it's your first time in the chat, if you're still in the chat, like, do you mind if I ask, what do you do for a living? Are you a student, or are you a grad student, or are you just basically like a person that's already working full-time in, like, you know, in society, and you're just basically love math and physics just for like as a hobby? Because that's what I am. I basically look at math and physics as like a hobby for myself. If the differential length elements of the previous section serves as a prototype for the quantity of the transform is, you may be wondering if there's a similar prototype for the covariant quantities, and you can answer the question by considering the quantity such that is change the temperature with distance, degrees per meter over a region. Unlike differential length element, which has dimension directly related to the coordinate dimensions, quantities such as the gradient and have dimensions that include the inverse of the coordinate dimensions per unit length, rather than length in the case of spherical coordinates. For every page I read, I need at the very least 4 pages from scratch work to understand. That's fair. That's fair. Yeah, I'm totally gonna continue reading this book like during the weekend. I mean, I also am planning to get into the exercises you assigned for us yesterday, Sascha. So that way I can actually like play with the transformation matrix with those coordinate systems. Because I think that's the thing we don't do enough in math, is just play with it. I think playing with math is like just as important as like actually being able to do math. Let's see, imagine a scalar quantity such as temperature or density whose value at various positions is given by the function f of x, y, and z. The rate of change of that quantity is f over df over dx in the and we already know that. It's reasonable to ask how these rates of change vary if the coordinate system is changed. To answer that question, you can proceed as if we did for the differential length element. Use the chain rule for partial derivatives and then employing the index notation as follows. Okay, so we have... Okay. Jeez, and this is only this is only three dimensions. This is only 3 dimensions. And I remember for like, I think for like general relativity it's 4. Oh, we finished the study session, guys. Ooh, my brain is like filled with so much knowledge, but at the same time it's like probably I can like probably the entropy in my brain is like making my brain hot. Well, that would do it for today's study session, guys. Hopefully you enjoyed it. I know we did a lot of reading this week. We didn't do that many problems, but I actually found this part really exciting because it was like I was reading it and I was doing my best to understand exactly what the author was telling us from both books, actually, from the Covariant physics book as well as this book. And, you know, like, I'll probably continue on learning more about vectors throughout the week. So, yeah, if any of you guys, like, basically love vectors, like, if you're watching this on YouTube, like, put it in the comments down below, like, on what you think about vectors or what I missed, like, if you've been keeping up with the content for this week. Okay, guys, for those on Twitch, I will put up my YouTube channel for you guys if you would like to subscribe in case you miss any future streams, you know, because I know people are busy and, like, you need a like something to create atmosphere to allow you to work efficiently. So you can check out my content on YouTube if in case, like, you want, like, I guess a little productive stream on in the background in case you need to work on something. But my stream is not live, so you can check out those. In addition, you are more than happy to join the Math Spell Book Library Discord server. Please join us. That way we can exchange ideas with one another, learn from one another, and perhaps, like, maybe like when we talk to one another, like, if you're stuck on a problem and, like, we start talking and then randomly the solution just pops up in your head, like, you know, that's one thing to, like, keep in mind. Like, that way your brain just gets to rest and then suddenly you came up with the idea to the awesome question you've been researching. In addition, I will also be streaming on my Uncle Talks video game channel. That's basically where I play video games and stuff. So if you would like to follow that channel as well on my other Twitch channel, you're more than happy to do so. If you're watching this on YouTube, all the links will be in the description down below. And like I always said, like, you know, drop a like, comment, and subscribe if you're watching this on YouTube. If you're on Twitch and you like math and physics, as well as, like, a productive stream to keep you going, consider following the channel. Really appreciate it. And if you feel much more generous, if you have Amazon Prime and you have a free Twitch sub that you would like to use, it doesn't have to be for me, it could be for any streamer that you want to watch, consider, like, subscribing. It helps out the channel, and, you know, it motivates me to continue streaming more math for you guys. Let's see here. Hold on. I want to see. Can we raid someone today? Oh, the Academy of Useless Ideas is streaming. We can give them a raid. So let's commence. So I will do the raid command for you guys, so you can copy and paste that if you like. So copy and paste that, and we will do the raid command for the Academy of, oops, didn't mean to separate it, Academy of Useless Ideas. Okay, the raid has been set up. Alright guys, thanks for joining me today, and always remember, everyone is precious. You guys are just as precious as everyone else, and I will see you guys on Academy's channel. So take care, guys. Bye-bye.